to have It's our pleasure to have Dr. Arpan Kusari to join us as a speaker today to talk about his work on benchmarking and breaking context bias in domain adaptation for object detection. Dr. Kusari is a research faculty at the University of Michigan Transportation Research Institute, and he also serves as faculty member at the Robotics Department at Michigan Institute for Data and AI in Society. His focus is on transportation safety, artificial intelligence, advanced sensing systems, and his work bridges both fundamental engineering principles and practical applications that enhance the vehicle autonomy and roadway safety. So his work has centered on the development of sensing methods, simulation, modeling framework, and robust machine learning algorithms in transportation context. And he has been principal investigator or co-principal investigator on numerous high-profile grants, including large-scale projects sponsored by Ford Motor Company, National Highway Traffic Safety Administration, Toyota, and funding for up to $10 million. And his principal projects address challenges such as developing comprehensive methods and metrics for vehicle performance evaluation and safety monitoring. Before joining University of Michigan in 2020, Dr. Kusari was a research engineer at Ford Motor Company, and he has contributed fundamental projects in the development and safety assessment of automated driving systems and advanced driver assistance systems. So the floor is yours, Arpan.
Okay. Thank you, Manshi, for that introduction. I would like to talk a little bit about myself, if I can. If this changes, yes. So I did my PhD in civil engineering. So I come from a very different background than most of the other people over here, like who do AI related work. I come from a robustness and uncertainty quantification background. So after I did my PhD was on LiDAR mapping for surveying applications, and then I got hired at Ford. So that's my James connection as well. And from there, at 2020, I moved to Umtree. So I have both industry and academic background. Um, as I was saying, so I have taken that robustness aspect of it, the uncertainty quantification aspect of it into AV, which I've learned on the job mostly. These are four verticals in which I work. Of course, I work beyond this, but this is more of what I have done and what I want to do. So sensors, LiDAR is my first love. So calibration, how do you do calibration when it's targetless? Can you do some guarantee on calibration? How do you operate under uncertainties? One of the things that we have done is if you can simulate cracks on the glass, can you still kind of, first of all, what does it do to the detection algorithms? And can you still do detections? Can the detections be robust? And then the simulating adversarial weather conditions, that's quite a popular topic, but we are trying to take a look at, rain. How does rain look on a camera image? This is very different from what Unreal Engine tells us. Um, then in perception, I have done a lot of work on intelligent compression. Intelligent compression, we are trying to look at if you are trying to compress data of foreground objects and background objects when the car is in motion, how do you do that? And then detection and tracking under out of distribution. So in out of distribution, we are trying to look at how can we tell out of distribution without having any examples of OOD. And then the last one that I'm looking at is robust tracking. So how do you do robust tracking where there is occlusion involved? In decision making, I'm working more in the robust decision making under uncertainty. So if you have uncertainty coming from sensors, from perception, how can you still make a decision which is robust to these kind of errors? The other thing that I do work on reinforcement learning, I don't work on the actual development of method, but what I like to work on is the coverage assessment. So if there is a training that has been done, has it trained properly on all aspects of the simulation environment? For example, if it's a map of a city, then does it know how to go through the roundabout? Because most of the times we do randomization and we hope that it actually encompasses everything. And finally, combining model-based and model-free approaches. That's another very popular topic. So one of the things that happens is simulation is the last vertical, but simulation is just feeding into these three. So I use simulation more of like, try to create the infrastructure for doing the other three verticals. So let's get into today's topic. I This came about because of a project, and in that project, I was talking about the ground truth trip recorder, which was a project that came from NHTSA. One of the mandates was that we needed to develop an object detection model, and of course, couldn't spend the amount of money that a company spends to build an object detection model. So the two options were build one or buy one, or even use one, which is like an open source one. So we decided to build one because we could then change and tweak it. And one of the biggest challenges we were facing was how to train. So we actually looked at simulation platforms. So started training in Carla and then tried to fine tune it in Kitty. So that's where this topic comes from. So if you talk about a domain adaptation, what it means is exactly on the left side of the image, you have different environments, different weather conditions. And this is actually from Waymo data. You have sunny, where it is probably trained on, but you can have rainy and at night and night and rain altogether. So the idea is that if you have a source, let me get my laser pointer. If you have a source domain and you have an object detection or classification, or any sort of model that you have trained on, and the idea is then you are wanting to like impose or use it in a target domain. So then the question becomes how can you adapt that particular object detection model from a labeled source domain. So in the source, you have labels, and in the target domain, you don't. So how do you actually adapt these? Now, why is it important? It allows the detection models to function accurately and reliably in novel environments. Of course, you have to make it work. That's engineering. And so you have to kind of do this for any sort of object detection model that you train. Um, Now, the question becomes how does DAOD work? The way it works is it aligns the foreground features. So, suppose you have vehicles in two different domains, in the source domain and in the target domain, and you are trying to force these features to be the same so that the model learns that there are certain features which are invariant. But the problem becomes that even the background features are changing. So if you look at night and day, those background features actually create a problem. No, in order to know whether this was a problem, we actually created some toy problems. It's not so much of a toy problem, but you will understand. This is a cityscape data set, which is a very commonly used data set. I think it came from one of the, I think it's an European data set. But what we did was very simple. What we did was we removed the road and we removed the sky. And then what we measured was the loss of information. The loss of information we got was minus log delta IOU. So essentially, what is the difference in logarithmic units? As you can see over here, this is bounding box area. And as it moves towards the small objects, there is a whole lot of loss in the without road part. But without sky, it actually does pretty okay. It doesn't have much of a problem. So there seems to be some sort of association between the background, which is road in this case, and not with the sky, right? So that kind of tells us that the background has some characteristics. It's not just blind background, right? The other thing that we did was we actually trained two models. This one is trained in yellow V4. This one is trained in yellow V11. This one is trained on Kala dataset. This one is trained on cityscapes. And then what we did was eigencam, which is basically showing what is the mapping. So essentially, which are the regions that could be highlighted as the features that the model is looking at to infer the object. So essentially, even if I don't know how well it is being shown, but these are the two objects that it is detecting, but these are the features that it is deciding on to tell whether these objects are the ones that it should be detecting. Similarly, in this case, it actually looks at the vehicles. You can see those vehicles drawn over here, but it's looking at the background primarily to actually tell that that's an object. The other thing that we did, so we did quite a bit of motivation because we were not convinced that this was a problem. But then what we did was we took this data set, we blacked out the entire road feature. And then what happened was it switched off the detection of two vehicles. So three out of the four were being shown, were detected in the first image. Only one was detected in the last one. So it decreased the detection quite drastically. So at that point, we were like, we felt like this was a problem, and so we wanted to know what does this challenge create, right? So what is context bias? So context bias is nothing but the foreground and the background are associated. And because of this association, once the background changes, the foreground also gets switched off. So even if you have the same object, you have trained on the same object, that will create problems um, for like when the domain is shifted. So it learns to rely on some sort of association which is not true, right? So it doesn't need to know, like if a vehicle is in the sky, I will still detect that it's a vehicle. Then I'll be very surprised how it got to the sky. But the fact is, first I will detect it's a vehicle. Here, it almost cannot detect it's a vehicle because it's in the sky. So that's a problem, right? It's kind of an opposite problem. And it fails to detect objects in the new or unusual context. So if I have trained that a vehicle is on the road, if it's on the grass, it will stop detecting. And it performs poorly when background changes. So any kind of domain shift, it has a problem. So we go from this to what exactly is the mathematical problem. And bear with me, this is the only slide which will have some sort of conditional probability. But the idea is that you can write the features. So if this is an object, and given the features you want to detect if it's an object, the features can be broken down into foreground and background, right? And essentially, this can also be written as F and B or B and F, where so I either it can learn O given FB or O given BF. The idea is that it actually makes it a lot easier for them to learn the background features because background features is a lot smoother. So if you think of the road is not changing a whole lot, whereas the vehicle is changing a lot, right? So it becomes much easier to learn the road. Now, there are some prior work where they have actually talked about this, right? What they have not done is they have not quantified it and they have not shown it in terms of domain adaptation because the domain adaptation is one where it actually matters the most. That the background features is always changing for domain adaptation, right? So for a new domain, background features will always change. But the prior work has almost tried to force the foreground features to align and ignored the background features. So the question becomes how important is this, right? Like, is this something that we should be worried about? The motivation slides tell us that yes, we should be. Now, there were three questions that we actually decided were important in this case. The first one was that if are these inadvertently learned? So essentially, is it always happening that these associations are being formed? And is that an artifact of the model itself, right? So if it learns these spurious features, is it learning, is it trying to predict, like improve on that performance, right? And so it's not understanding what is foreground, what is background. It's just learning it because it's part of whatever the model is saying, right? Uh, and that makes it a very difficult problem for us. And then the next question is there a causal relationship between these associations and object detection? What I mean by that is there a graph that we can draw? So let me explain this figure first. If X is an image, F and B are the features, and Y is the output, you can draw a really nice causal graph, which looks like this. It goes from X, goes from F and B, and finally goes to Y, right? Which is the output. Generally, if you have a neural network model, you can remove the X because the F and B are learned on the X. And so F and B together influence the Y. Now, F should not have any kind of association with B when you are trying to extract the features. Yes, I know that road and vehicles happen on the road, but we can kind of remove the vehicles and the road. So they should be independent. Now, the ideal case is that the foreground features are the only things that are influencing Y, the output. But what we find or what we are seeing that is something that we are going to check out is that the F and B are getting associated at some point, and that is influencing Y as much as the foreground. And finally, our question becomes, can we actually remove these associations, right, through some sort of do operation? And finally, we have not talked about the DoD part, if you notice. So in the third question, our idea is that what is the impact on DoD, domain adaptation, and how can that effect be quantified, right? And for that third point, we actually use something called a domain association gradient that we have actually proposed. Now, the contributions are this is it systematically investigates the foreground and background associations that can create the context bias. It introduces new protocols to measure the background masking using some sort of image level and class level, so feature space level quantification as well. It applies causality framework, so some causal analysis and do calculus to quantify the influence of these associations. Um, then it we propose a novel metric to understand or quantify what is this amount of change that is induced when we go to a new domain of the association piece, right? And finally, you have practical recommendations for a robust DoD. Now let's get into related work. By the way, if anybody has any questions, I cannot see you guys very clearly because I'm sharing. If you have any questions, please let me know. I can answer at that point.
Or feel free to put them in the chat too, everybody.
Yeah, if you're managing.
I'll manage that. Don't worry about it.
Yeah, yeah. Okay, so let's talk about the related work. So context bias is not new, right? We have not invented it. It was there. Um, and one of the things that were there was the numerous studies show that it can over rely on that background context. So it actually relies more than it's supposed to. So there are like, numerous papers that have been detailing that. Now, one of the differences is that so in this case, the first work that we could find that we have taken inspiration from was one by Toralba, which actually looked at modeling these associations in a graphical model. Then comes Choi et al. In 2012, where they use a graphical model using conditional probability, so they constructed these associations. And in 2023, Liang et al. Looked at background influence and how much these background influence actually are are dependent on making an object detection. They used fashion data sets, so like fashion of clothes. Um, and finally, it's our work. So as you can see, they do not quantify or analyze any causal impact in the domain adaptation space. So ours kind of looks at this domain adaptation setting specifically. Now, in terms of domain adaptation, a DoD kind of work, there are three main, if you think of three main branches. The first one is feature alignment that I've talked about. What it does, it almost forces the foreground features to remain together and repels the background features. So essentially, it's actually reducing the distributional shifts. The second case is trying to generate synthetic images. So if you want to create synthetic distribution to bridge those domain gaps. The third one is to use self-distillation. So there is a teacher model, there is a student model. The teacher model predicts a pseudo labels on target domain. So those are the three main categories. So you will notice that none of them actually look at the background part of it, the context bias part of it. So one of the things that we had to do, we did a lot of experiments. We had to do a lot of experiments because people wanted to know whether this could be true for every kind of data set, every kind of model. So in this case, we have looked at different kinds of experimental setups. We have cityscapes, as we have talked about, different kinds of cityscapes. We have Kitty, and then we have virtual Kitty. And we also utilize the background 20K data set, which we'll talk about in a little bit. In terms of models, we use this model ALDI++, which is a domain adaptation model. It's the state of the art right now. We also use the normal ResNet 50. We use an efficient net because it's supposed to give us the small, it's a smaller model. And YOLO V11, which we use for a little bit, a small number of experiments. We could not use it for everything because it has some layers which do not have it does not do backward pass very easily. Um, in terms of evaluation metrics, we used a map, which everybody uses. It's an IOU threshold of 0.5. And we also utilize drop rate. So how much is the change in detection probability due to background masking? So this one is the first evaluation baseline. This is done to kind of, that's where we start from. So there are three main data sets that we have trained on, Cityscapes, Kitty Semantic, and the virtual Kitty. You will notice that most of the cases, ALDI++ is the one which works the best, other than some version where YOLO actually performs pretty well. There are lots of places where we could not make it work because of unmatched classes. But generally speaking, you can see that ALDI++ provides the best case result, and the efficient net, because it's a smaller model, actually performs the worst. Now, the first thing that we did was removing the background completely. So the way we did it was we have the foreground objects and we superimpose them on some sort of background. So if you can look at the right side image, it's a completely different background, and we superimpose the foreground objects. So the way we did it was we took this BG20K, which is a background image data set, and we have the number of target domains, right? Set of target domains. So for each foreground object, then we randomly sample a fixed set of background images, synthesize the image by placing the foreground object onto that background, and then we apply the trained model on all these synthesized images and measure the detection performance. We did it for 6 different trials just to make have some sort of some sort of confidence bound. So what we
Arpan, hey,
sorry.
Arpan's on here. Hey, can I ask a question about the definition of background and foreground?
Yes, please go ahead.
Yeah, could you define what background and foreground is? Like, I'm trying to understand if I think of like a theater production, the foreground might be what's on the stage, and the background might be like what's, you know, fixed in the back. But I could also imagine maybe what we're talking about is things in the image frame that remain fixed, and that would be background. And then things that are moving are foreground. So can you help me understand like how, yeah, in the context of this research, how do we define background and foreground?
Foreground is what we are interested in. Now, it could be static. It could be a traffic sign, which is static, but we are interested in it. So it could be the foreground of that image. So anything which we are interested in, so any class that we are interested in, it be vehicles, pedestrians, traffic signs, stop signs, could be our foreground. And background is anything that is like not of our interested classes, right? So
I
we
see.
we have a very broad definition of foreground and background in that case, right? It can be static, it can be dynamic.
I see. So I probably shouldn't hyper focus on the words foreground and background, but rather when you say
Yeah.
foreground, it's objects we're interested in, and background is just like context for the objects we might be interested in.
Yes. Yes.
Okay. Okay, thank you. I'm glad I asked.
Sure. Uh, so yeah. So there is something in the chat. Oh, okay. Um, so one of the things that was interesting is Audi++ still performs the best. Even with the background removed, it performs the best. But the models that are trained on Cityscape, it shows substantial drop. So if you looked at the previous, if I look at, it was around 87, 70%. So it was big, right? It comes down to around 47%, 43%. So it comes almost like 40% of difference, even though it's performing really well. So if you look in terms of just pure performance, Aldi++ is great. By the way, Aldi++, it actually looks at, it trains using the label data from source and target. So it actually forces them to be similar, right? But if you look at the percentage drop, it's actually pretty bad. Um, do I look like a mythical figure with a halo? Because that's what I am seeing myself. Sorry. Um, um, so in terms of So yeah, Aldi++ kind of looks very, it exhibits greater degradation, right? On different data sets. So KST is one where actually REST performs the best. Um, the other thing is that models that are trained on Kitty and virtual Kitty, they also have a lot of decline, right? Like, so essentially, you can see that it's not as much as the Cityscape one, but you see that the amount of degradation that occurs is pretty large. So yes, background removal creates a problem, but that's on the image front. The next question becomes, could we do it in the feature space? So if we don't change the image space, but we change the feature space. So what we did was we actually, and in this, let's talk about the detection drop. The detection drop is counted as dropped if we have a predicted class which changed. There was a loss of information which is greater than one. So one being a logarithmic unit. And there was a prediction which matched a different ground truth object. So in this, all these different cases, it would be counted as a detection drop. So now how do we change the feature space? We actually looked at for each model, we again did it for 6 experiments. For each model, for each image with some semantic ground truth, we did a standard inference, right? Stored the number of detections. Then we actually looked at the shallow feature map. So in case of ResNet, we looked at 2.2, for example. We could have changed the shallow feature map, because if you do it for shallow feature map, it will propagate throughout the entire layer. That was our idea. And then we actually computed the detection drop. So like, how much of these is changing. And then we store all of them. And finally, we conduct a Wilcoxon signed rank test. The sign rank test is because we cannot assume normality, right? So that's why we actually use for the Wilcoxon sign rank test, which is a non-parametric test. But this was done because we wanted to see if it was propagating through the layers of the neural network. So if we could pick up a neural network, change the feature map of that neural network, of that particular layer, does it actually create the same kind of problems, right? So one of the things that we saw was that, and this is very interesting, that a person has almost a very good association with building, road and car, and car and building, which was very weird for me. A bicycle had building, sidewalk, and road. So you could see where they were picking it up from. Bicycle was also kind of having a good kind of association with vegetation, as was a rider, right? But you could see that there was this drop rate of the foreground and the background. So here, Scott, you can see that the background could be building, road, sidewalk, vegetation. We're mostly static, but it doesn't need to be static. And foreground is person, rider, bicycle. So anything which is kind of something that we are interested in. And the drop rate, you can see all the way from 0.22, which is in the logarithmic scale, to 0.09. But if we do this Wilcoxon rank test, which is basically just ranking how many of them have a significant drop. So anything that was more than 8% of difference in the IOU, we actually took that as the number of ones that were interesting and were significant. So what we saw was that ALDI++, even though it was trained with a domain adaptation perspective, had the maximum kind of effect. So in most of the cases, other than the virtual kitty ones, at least in the cityscape one, the ALDI++ was the one which had the most amount of changes or significant drops. Um, the virtual kitty ones are very interesting because it is constructed, it's a virtual synthetic data set. So it is constructed with some temporal correlation and spatial correlation in mind. So for that, the ResNet was the one which actually performed the worst, or it's actually on par or very close. Um, so what this actually told us was that it's not enough that the model has the or forces the foreground features to lie together. Even if that is the case, if we perturb the background, those domain adaptation models can also have a significant drop. So that was really interesting to us. Now, if we look at the causal analysis, so if there are, like what we wanted to know is the association, right, of the foreground and background with respect to the activated background region. So essentially what we wanted to know is so suppose we have a true object and the cam, which is just telling what is the importance of that pixel, right, in generating that object. If the cam has some version or some portion of the background, right? So in this case, it's very difficult to show, but what I would tell you is that if there's a background region that is being activated, we actually tried to go from no background, which was bin 1, to all background that is activated, which is bin 9. So we basically actually binned it from 1 to 9. And so it's increasing in area of the background. And what we wanted to know was how much of the area in this, whatever bin it is, if we switch it off, what are we getting? So if we take no background, what are we getting? If we take, increase the amount of background, is the drop rate changing? So that would just give us a sort of, causal interpretation or influence, right? So because this is activated background region, we are not like removing the entire background. So it was really interesting because, first of all, what we wanted to see was how much of the foreground and how much of the background is getting activated. So if you look through the layers, it shows that for foreground, so this is just the foreground ratio, right? So the hit ratio is ratio of the captured background to the total number of foreground. So for total number of foreground, if it is 1, then there is 14, so it's in a factor of pixels. So there are 14 multiplicative factor of background that is being activated. So it's a large number of background that gets activated in the rest too. And it increases as it goes down the layers because it kind of aggregates information. And there we are seeing the associated and the non-associated. So the non-associated is where the cam is not getting activated, right? So that is getting smaller. Now, the interesting part is as it goes through the bins in all of the cases, the bin 1 does not have any background. And so this is basically showing the drop rate. So you can see that there's a huge drop when there is no background, and there is almost no drop when there is all background that is activated, which we wanted to see. But the thing that was very interesting to us was the sharpness of it. So if we include a little bit of background, which is bin 3, it goes from 0.65 drop to 0.14 and 0.62 to zero point 0.1. So it actually does really, really well when it gets a little bit of the background. And this is the case in almost all of these models, right? So that shows that you need to have some background context. If you don't, it actually cannot figure out what kind of foreground object it is. And that was very, very interesting to us. Um, Now, the last part of it was to quantify that how much of this is based on the domain adaptation. So if there is a causal effect. So what we thought about was let's remove the background. And once we remove the background, if there is detection fails, then there is a car feature has an association with road, right? If there is a detection, then it's a confusion matrix. But the false negative and the true positive, we could not figure it out. So it has like unknown association. So we have to kind of remove it. So in all of these cases, we have to go through source domain, target domain. There is non-association, there is association, right? And based on that, we can average the features of foreground and background. Now, all this is saying is that we actually looked through the source and target and separated it. And once we separated it, we could actually get the foreground and the background average. Now, why did we do that? We did that because we wanted to calculate this gradient. Now, this gradient is nothing. If you think about it, it's just delta y by delta x. Now, what is the delta x? The delta x is the difference or the distance between the foreground and the background. This is the MMD, which is the mean maximum discrepancy. So that's just saying that how much of a separation is there between the foreground and the background. Now notice that we have added the foreground to background and the background to foreground and subtracted the foreground to foreground and background to background. So the reason for this is we wanted to see how much was the distance between the foreground and the background. And we want to remove the foreground to foreground and background to background. So similarly, gradient S, we call it gradient because it is truly delta y by delta x, right? So there is a gradient x and a gradient t. So that corresponds to the source and the target. Once we have the source and target, you can tell whether the gradient t is greater than the gradient s or not. And based on that, you can also do the delta x. So essentially the MMD between the XF and the XB. So essentially, how much is the separation between the target and source and the target, right? So you can do it for F to B, B to F, and for associated and non-associated. And from that, we get this really nice sum, which is AA, and sum NaNA. And that just tells us, okay, there is a separation, there is no separation, right? And from that, we see that this one is really interesting to us, again, because this is gradient S and this is gradient T. So for each of those cases, we see that the gradient S, which is the source domain drop rate, is much higher, right? So we have a gradient which actually lowers. So the gradient, oh, sorry, the gradient S is lower than the gradient T. So gradient S has a lower drop rate as opposed to the target domain, which we wanted to see. So the actual separation is always like lower when we go to the new target domain. And that all that means is that the target domain, whenever the background features are changing, it's actually bringing down the detection accuracy. And now we can actually quantify it. So for each pair of the foreground and background, we can quantify how much of a separation there is between the source domain and the target domain. And from that, we can give this beautiful figure. We can also create this different kind of cases. And this is again a Wilcoxon rank test. So we see in most of the cases there are three cases. So this is significantly lower, this is significantly higher, and no difference. Most of the cases it's significantly lower, and that's what we wanted to see. How are you doing in terms of time?
You have 10 minutes, maybe 9 minutes, but that includes the Q&A, so,
Okay,
if you want.
so 2 3 minutes probably. And in terms of the sum AA and sum NaNA, that's just telling us how much are the associated features smaller or the non-associated features smaller. So we see that the associated features are smaller. That's what we wanted to see. That it always has lower MMD than the non-associated features. So both of these results, what it tells is we can quantify how much of a change does background, when we change the background, how much of a change it actually creates on the foreground, right? And the detection accuracy for that. So this was a quantification. This is the first time we could provide the result of domain adaptation. How much of a change does it actually create? So the question becomes, is there a solution to this, right? Can we do something else? So we figured out that this occurs during the feature extraction process. So our idea was, can we do something about like, does it have to do with the aggregation of features? So what we looked at was the pooling operation. Now, the pooling operation, what it does is it aggregates features constantly. So if you have a foreground, suppose you have a vehicle and you have road, what it's doing is it's aggregating the road features along with the vehicle features. And so when you create a separation between these two, that will help, because now what you can do is, instead of pooling all the features together, you are pooling the road features separately and the vehicle features separately. And that can actually try to kind of remove that association between the foreground and the background. So what we did, and this is the second part, I will not talk about much about this, but we actually found a way to look at the true mask if you will, and see how much of a difference does it do. So essentially, when we change the background, we found that the ones with the correct mask or correct mask actually does the best. It doesn't change that much in all of the cases that we have tried, and otherwise, and it's all across the models, even with transformer based models. And so what we wanted to see is that, is pooling where we are actually separating the features something that actually does the best case scenario, and it actually does. Now, the discussion from it is the object detection models, if it's a CNN based model, it'll try to aggregate features, and based on that, it'll not generalize well across domains. We actually show that creating a pooling operation can lead to robustness. Now, the question is, can we utilize these associations effectively? So, during the extraction process, we should not use these foregrounds. But after the extraction process, can we utilize these to say, like, a car should not be in the sky? Something like that. So, that is our future work that we want to work on. And thank you.
We have a few minutes, so maybe we can open for some questions. Are there questions from the Zoom audience?
Sure, I'll ask the question. Arpan, can you actually go back to the pooling idea? And could you explain that once more? I think I didn't fully understand it.
Yeah, I kind of brushed off it.
We spent like 15 minutes understanding the problem and maybe a couple minutes understanding the solution, which is great. I think it is to understand the problem. So yeah, could you just explain this again?
Yes, let me explain to you by just giving this binary mask. So if this is the activation map, this is the binary mask, right? What you can do is, instead of saying that I will aggregate all the features together, you are just saying that I will separate out wherever the foreground is, and I'll aggregate them at the same spot. And for the background, I'll aggregate those separately. So what it does is, in the feature extraction process, you are not entangling those features together. And the idea is that once you average these, it turns out that they can separate out the foreground and the background neatly, even under like extreme sort of degradation, right? If the background feature is completely different, even then it does not have a problem, because now it has learned to actually look at the foreground only. Now the question is, how do you actually get this foreground mask? Because that is a magic, right? Which I have not explained. And the idea is that you use something like a segment anything, or you actually incorporate that into your feature extraction procedure, where you first create a boundary and then you do the feature extraction. It's a chicken and egg problem, because how do you create a boundary without feature extraction? That is something that we have developed. It's in review, so I hope the reviewers agree with us. But the idea is this, right? Like, you have to separate the features of foreground and background so that they don't get contaminated. Right now, what is happening is they are getting contaminated.
You.
You don't look too convinced, Scott.
Thanks. So, okay, so if we don't have more questions, let's maybe thank our speaker again. Or if you have more questions, you can follow up with Arpan after the thank you. Thank you very much.
Sure.
Thanks.
Thanks, Arpan.